Now it's free for all. Whatever. Ask me anything. What do derivatives do? They compare neighboring values of the field to myself. I have my identity. I am I, and that's replaced by the unit in the definition of derivative. And derivatives can be generalized. I've defined this on a hypercubic lattice. That's called a graph, meaning that I connect points by links. And this particular graph is a very familiar graph because it shows up in crystallography. But in much more general setting, for example, you work for Google and you have to do graph your data. You have to give it graph structure saying this cluster of data is, the Jennison faces are clustered close to the Brit faces. Then there is a link between them. Then you produce abstract graphs, meaning, they give you relationships in your data sets, which are much richer than this particular very simple discretization of space-time. In that case, you can still define derivatives because you still want to compare what the neighbors are doing. How much does it cost to be Jennifer versus how much does it cost to be Brad, or some other cost function can be assigned to this, or how much error I'm making by misidentify Jennifer for Brad Pitt. So this notion of derivative as comparing to the neighbors generalizes to very, very large sets of what we do in modern large data analysis. But in physics, traditionally, it tends to be just a device to implement what Euler meant by derivative and by integral.